Okay, so next up we have someone who doesn't maybe need an introduction, but he'll get one anyway. So it's my pleasure to introduce Pierre-Hugues Stefanuto, who's from the University of Liege. Most of you know him. It's really rare that we get opportunities to present at this meeting, even though it's obviously our favorite one. But when the opportunity arises, I think it's always nice for us to remember that we all pretty much started by presenting in this community. So with that, I'll let PH take the floor.
Thank you, Kate, for the kind introduction, and thanks the committee for selecting my presentation for speaking with. No, but like as Kate mentioned, it was like we had the opportunity creating the program to present ourselves, and for me, I was like, yeah, you know what? It's been like since 2018 that I didn't present it during the workshop because basically we have like other stuff to do during these 3 days usually. But I'm really happy to be here today and to speak about what we are doing with GC GC in the omics field and how we can like spread over like different parts of the omics field. So Michael did a really good job speaking about breast, and I will speak about more like what we can do with other type of matrices. But before to go there, so we have been speaking about the technique for a couple of days now, and I like to reflect on the technique, especially when I'm presenting GC GC in conference like metabolomics, where they are not all familiar with that. And I don't know if you know this technique, but it's called the Gartner Hype Cycle. So it's a way to evaluate where your technology is standing. So when I saw that the first time, I was like, Jesus, it's the story of GC GC. So 1990, John Phillips like created the techniques, did the first petroleum injection. Rob mentioned like we had a hump of unknown and now we know what is there. So expectation rise. And after like, we are like, okay, if we can do that for petroleum, we can do it for everything. So people try to use it. They try to do like a study where you don't just inject one sample and go into the details, but inject like different classes of sample with different like injection techniques. And having a hardware that is reproducible, and there, like, you fall down. Like, GC GC is not easy. Like, you need to have, like, a modulator, you need to manage to connect the colon and everything to make it work. Like, this started with a swiper, so you have, like, mechanical movements. Like, it was a nightmare. So Jeff always make the joke that when he went to CDC to work with John, it took him, like, an entire PhD to get one chromatogram. And he still have the floppy disk because, yes, they were using floppy disk with the chromatogram that he brought back from Atlanta at the end of his PhD. So the question is for me, like, where is GC GC now in like early 2024? And for me, when I speak the technique in general, I would say that we are reaching this plateau of productivity because the hardware is there. So now you can have an instrument that is not too complicated to use. Like for me, it's not like that much complicated than simple GC. It's a couple of extra connection, but now we have easy connector, like finger tight and everything. We even have high resolution. So I would say that's a bit more complicated, especially like you have the data side that you need to manage. Instrumentation is newer. So we are maybe like still on the slope of enlightenment because we have to bring it there. But you can do that for the field too. And when you speak about GC GC and you bring it in the field of metabolomics, like where is metabolomics now? And it's also complicated to judge because as Michael like just mentioned, like you have database, you have papers, and when you dig into the analytical part of it, you have, okay, list of compounds, biomarkers, but nothing is validated. Like it's not a biomarker, it's a hit on one of the library that you use for the identification. So there is work to do and to improve. So I would say the bottom of that was a couple of years ago when we are saying like, we will never be able to use metabolomics. And now they put in SOP, they put in guidelines to help you to do the work correctly and then bring back QA QC into this type of study. And so omics. So for me, it's really a domain that is mostly mass spec people. So when you go to metabolomics, it's mass spec people, like people doing chromatography, they do LC. And when you speak about LC with them, they consider LC as a really expensive injector. So they don't always see why we can improve what we are doing with separation on the top of that. And for me, if you do a better use of your LC, you will improve the quality and the annotation of your features, but you can also and especially do that with GC and GC GC. So today I want to speak about a specific project where we were doing serum analysis for colorectal cancer. So a lot of the requests that we have to do small molecule analysis in the context of cancer, and it's just because of the rise of cancer. So we screen more, so we see more, but it's also that our lifestyle, it's really influencing like the rise of cancer. And colorectal cancer is really linked to that. So people are eating more, moving less, and that's created a lot of problem there. So in the screening method that exists now for colorectal cancer, it's like the true definition of invasive. So if you want to detect a colorectal cancer, you go to a colonoscopy. I will not go into the details of the techniques, like you have a schematic there, but you don't want to go there if you don't have to go. So they created some stool-based screening methods where basically you can send a stool sample, it's analyzed through microscopy, and if they detect blood residue, you are bring in and you go for the full visit. And the problem of that, it's like, if you speak about clinician, stool-based is still invasive. If you ask someone if he would prefer to provide a stool sample or a blood sample, they will all go for blood sample. And for the blood, they need to stick a needle in your arm, but still, and I will go for blood too, like 100%. So there is space for alternative technique. And to be honest, no blood is considered as non-invasive because we have blood check all the time. So getting an extra tube is not something that will block people to get into the hospital and to get a screening. So yeah, let's do it with blood. So I will call blood minimally invasive. So if people are scared of needle, I will understand, but I will use this term. And after you can like screen and see what you can get out of it. So here we got this serum sample from the hospital, and we decided to do two different approaches based on the same instrumentation. So we went for what I will call the global metabolomics. So we did MSTFA derivatization. We shoot it on the GC GC, and we see what we can see across different chemical families. But based on the literature, we know also that colorectal cancer provoke a high degree of inflammation. So we say inflammation, perturbation of the fatty acids. So we had what I will call a semi-targeted lipidomics method, where we will process the serum in order to don't see as much as we can, but see as much as we can of the fatty acid present in the sample. And on the analytical side, we were like, okay, omics equal large sample set. So we decided to see how we can better fit GC GC in this workflow. So we first use a Pegasus 4D for what I will call the large scale screening. So every single sample was injected there. And after the first phase and the identification of feature of interest, we shoot again the same sample on the HRT. And the reason is why is because, as I say, low res, like peak of productivity, we know how it will react. We know that we can run it. We know that we will have not too many issues to maintain the good chromatography that we speak about this morning. And the HRT, when you want to do like a lot of sample, it's extra work to make sure that everything is stable. So we discussed this morning with Michael about like the issue of drift on the mass spec and everything. So we didn't want to go that road. But we have the two instruments and we still want the power of the two instrumentation. And something that we noticed is also when you take the time to set up your system properly. So I don't know if you can clearly see that this is the exact same sample injected on the two system. And basically, using the same colon and adjusting a little bit the length of the secondary colon, you have really a transfer between the two. So you can get a compound that you detect on your low res, and at the exact same position on the image, you have the same compounds with the high res, and you have the accuracy there to identify it. So we don't need to inject everything on the HRT, because when we know where the feature is, we check on the replicate injection on the HRT and we say, yeah, let's pull out the information about identification. The only limitation that we have here is the fact that when you do high-res, you have a limit of detection that is higher, so you may have some compounds that you cannot detect there, but we can live with that. So in this study, we had 3 groups. So we had adenocarcinoma. This is the really nasty cancer. You don't want to go that way. You have adenoma, which is like a benign growth in your colon. Usually it's not treated because they don't need to intervene. And we had like LC control. And something that on this project I discovered, it's like there is a difference between the population and the analytical count. And when you speak about clinician and you give them a price for the analysis, it's really important to like explain it like in detail. So they will imagine that we have a population of 64, so I will do 64 analysis. But this is not the case. For example, to reach the 64 analysis, I injected like more sample because some of them were just not stored properly. The serum was degraded and we couldn't use it. I have my QC for like the baseline of my QC chart. I have the QC that I inject with every batches. It's serum analysis, so I can inject my SERUM to get more robustness in my identification and on my workflow. I have standard ID, so I do fatty acid. So the fatty acid of interest, I can purchase them and shoot them too. And I reached like more than 100 injection, but I did 2 different sample preparations. So for 64 patients, at the end of the road, you inject like more than 200 samples. So that's explain why sometimes like it's complicated for reviewers or for clinicians to understand like how much work it represents for the analysis. So going through this explanation and the design of this type of study, like as I mentioned before, now there is an initiative. One that I really appreciate is the MQuack, where they are really trying to provide guidance for that. So some members of the community are really active into that. There is no working group on GC. James, I know you are there too. So we are really trying to help people to say, okay, try to go that way. So you will like overpass some of the limitation and difficulties that we know you will encounter if you don't pay attention. So today I will focus on the semi-targeted lipid screening, and it's a really basic sample preparation. So there is different way to extract fatty acid. We took this one because it's easily automatized, and the only thing that I want to focus you to put your focus on is the volume of serum. So why also is it non-invasive? It's because we only use 25 microliter of serum. And why is it non-invasive? Not because I will only ask a patient to give me 25 microliter of his blood, but these samples are usually coming from biobank. And so the clinician, when I say, okay, I need more sample, I want a bigger population, they're like, yeah, but I don't want to like waste my biobank for your fancy GC GC technique. So when I told them, you know what, you have 1 ml and give me 25 microliter, they are like, okay, that I can do, no problem. So this is also where we have to be non-invasive. It's not really for the patient again, but it's also like for the context in which you are working on. So the good thing about GC-GC when you do fatty acid analysis, it's you clean the space because you focus only on one chemical family. So you can use all that space to have structure separation. And with fatty acid, it's really nice because you have, when you inject that on a normal colon set, you have a grouping along the x-axis based on the C number, and on the y-axis, you have the number of insaturation. So you can really use your space to get information about the identification. So you know that, okay, my compound is probably a C18 and it's an isomer. I don't know which one, but I know that EF2 and saturation. And I have this information. I haven't even injected a single standard yet. It's just that it's structured that way. So let's dive into the processing. And on this project, we had a big challenge, is because we had a really inspired idea to say, let's try to use different like colon sickness to see the impact on the separation. And what we discover is when you use a really sick colon, even if it's siloxane with BF3 derivatization, you are just destroying your stationary phase. So over the run, you see the drift in retention time that appears there. And it's not like something like, oh, my colon breaks and I have batch 1, batch 2. I have this continuous shift of retention time. And I'm like, okay, I have software, I have tools, I can correct for that. But when you see a group of peak, as you see there, they are branch isomers. So when you will try to align that using the mass spec information, the software will make some mistakes because when you check two peaks side by side, they have the same fragmentation because they are branch isomers. So sometimes you will just shift from one peak and say 900% match, go for it. But it's not the same peak because if you can't, if you check the structure, you know that it's shifted. So there we had to manually address based on the standard that we inject, so importance of the QC, the drift of the retention time to make sure that we bring everything on the good side of things. So that was the nightmare. Let's come to the enlightenment. So when we took all these fatty acids, so here we detect around 40 fatty acids, and we plot them on the PCA, like we had a really good surprise. So we can clearly see that we have 3 groups, and we have the red one, so the really aggressive cancer that was like alone at the bottom, and the benign and the control that were separated but a bit overlapping. So clearly taking fatty acid was the good way to go. We knew it because fatty acid, inflammation go with cancer. So our hypothesis was already oriented, but it works. And it's also provide us confidence that the fact that GC GC is able to read this inflammatory information into the sample. So after that, we went for feature selection because we wanted to check also if we see like metabolites that are like linked in the same pathway during the inflammation process. So we wanted to reduce the list. And during this process, we did 2 approaches. So we did ANOVA and we used random forest as a feature selection method. And we obtained the same top 8 compounds of interest. And basically, again, we obtained the information that we are expecting. Omega-3 decrease in a patient with cancer and omega-6 increase. So again, this is the mechanism of inflammation that was present in the blood of the patient. So after we try to see in the development of this workflow, okay, how can I bring all this information together from the 2 instrumentation to try to be confident in the compounds that I have? So I know in which groups I am because I have the structure of the separation. I have confidence into that using my fragmentogram, but you can see that, for example, for the first line, the probability is really low. Again, I have a lot of branch isomers, so I cannot be sure of exactly the branching that I will go. So this is really something that I really like in Chromatoph. It's this probability column that for me it's more informative than the similarity score. Because if you have 900 on the similarity score but 10% on probability, yes, it matched, but it matched with a bunch of stuff in your library. So we had the retention indices that were like quite below what we were expecting. We had the mass accuracy when we were able to detect the molecular ion. So we have all this indication of identity that were really useful. And all the compounds with the star were the one that had the standard in the fatty acid mixture that we were using, so we can confirm the identification to an higher level. So when we had that, we were like, okay, now let's see how the data look like on the PCA with only these 8 compounds of interest. And this is what we get. So the structure of the PCA is changed because we have less dimensions. It's expected. We still have the same behavior with adenoma and control that are close, a bit overlapping. But on the adenocarcinoma side, we had these 3 little clusters that pop up, and we are like, where is it coming from? Like, is it batch effect that appears for these compounds? Are we saturating in this sample like the omega-6? So we went all the way. And finally, what we did, it's we cross this information with the metadata. And basically what you are seeing there is the staging of the adenocarcinoma. So you have stage 1, stage 2, stage 3, based on the inflammation level that appear on the PCA, even if it was not target of interest. It's just that we focus on a specific hypothesis that correlate with the clinical data. So the take-home message here, it's like, of course, multidimensional chromatography has its seat at the omics table, because I really think that this screening capacity, again, for non-targeted or semi-targeted analysis, and this increased capacity of identification of the compounds using these different metrics is really something that the metabolomics field needs to move forward. But that will come with strong QA/QC. So again, linking back to the group discussion that we did yesterday, this is how, for me, my main interest in GC GC metabolomics and fundamental development of SRM with John, like, connect all together, because with this type of mixture, I know that we can facilitate robust QA/QC in most of the lab where people are using GC GC. And of course, like, really this lipidomics screening provide us high classification between classes, stage information. It's a really simpler sample prep compared to MSTFA. It's basically you put the reagent, you do a liquid-liquid extraction. You can do that with a simple robot. And you can obtain a lot of information just by having all these features that appears on your chromatogram. So with that, I want to thank Kinjal, I should say Dr. Kinjal Bhatt now, that graduated last year, and she did this work as part of a PhD. Funding support, company support for the instrumentation. So thanks, Lico, for helping us achieving that. And thank you for your attention.